Alright, so let's end the section with an example with multiple chains of generalized eigenvectors corresponding to multiple eigenvalues. So let's consider this example. X prime is equal to 2, 3, 0, 0, 0, 2, 1, 0, 0, 0, negative 1, negative 1, 0, 0, 0, negative 1. So this is our matrix A. So to diagonalize it, or at least to try to diagonalize it, we solve the characteristic equation, which is determinant of A minus lambda I equal to 0, which means the determinant of this is equal to 0. Notice that this matrix is upper triangular. So the determinant is equal to the product of diagonal entries. So that means 2 minus lambda, 2 minus lambda, 2 minus lambda times negative 1 minus lambda times negative 1 minus lambda equal to 0. So this means 2 minus lambda squared times negative 1 minus lambda squared equal to 0. So the eigenvalues is lambda equal to 2 and lambda equals to negative 1. Both of them have multiplicity 2. Okay, so let's we have to deal with the two eigenvalues separately. So let's do that. So let's first deal with lambda equal to 2. Okay, so let's first solve a minus 2i times b equal to 0. This means 0, 3, 0, 0, 0, 0, 0, 0. There's a 1 here. 1, 0, 0, 0, negative 3, negative 1, 0, 0, 0, negative 3 times v equal to 0. Okay. The second row tells you that v3 is equal to 0. The fourth row tells you that v4 is equal to 0. The third row tells you nothing new. And the first row tells you that v2 is equal to 0. So the solution, so the eigenvector solution is the only free variable is v1, so 1, 0, 0, 0 is an eigenvector. So there's only one eigenvector. But the multiplicity is 2, so lambda equal to 2 is defective with defect 1. Okay, so if we draw the diagram, we only have one eigenvector. This is 1, 0, 0, 0. This is v1. This goes to 0 when you multiply by minus 2i. So to find the other one, because it's defect 1, so we know we have a chain of length 2. So all we do is solve a minus 2i times v2 is equal to v1, which gives you 0, 3, 0, 0, 0, 0, 1, 0, 0, 0, negative 3, negative 1, 0, 0, 0, negative 3 times v2 is equal to v1 is 1, 0, 0, 0. The fourth row and the second row still tells you v3 and v4 is equal to 0. The first row tells you that 3v2 is equal to 1, so v2 is 1/3. v1 is still a free variable, so the easiest choice is v1 equal to 0. So the solution is v2 is 0, 1/3, 0, 0. So that's our v2. Okay, so that's for the eigenvalue lambda equal to 2. So we do the same thing for lambda equal to negative 1. So we first solve a plus I times b equal to 0. So we get 3, 3, 0, 1, 0, 3, 0, 0, 0, 0, 0, negative 1, 0, 0, 0, 0 times v equal to 0. the third row tells you that v4 is equal to 0. The second row tells you that v2 is equal to 0. The two of them and the first row tells you that v1 is equal to 0. So there's only one free variable, which is v3. So the solution is 0, 0, 1, 0 is the eigenvector. v1 and v2 are already taken, so we should call this v3. So this is the only eigenvector. So only one eigenvector. So lambda equal to -1 is also defective with defect 1. Because the multiplicity is 2 and we only found one eigenvector. So the diagram is similar. So we have 0 with v3, which is 0, 0, 1, 0, multiplied by 1 plus a plus I. Because it's defective, so we know there's a chain of length 2, and with v4 going there. So we solve a plus I times v4 is equal to v3, which gets you 3, 3, 0, 1, 0, 3, 0, 0, 0, 0, 0, -1, 0, 0, 0, 0, times v4 equal to v3, which is 0, 0, 1, 0. Okay. Second row still tells you v2 is 0. The third row now tells you negative v4 is equal to 1, which tells you v4 is -1. And these two together with the first row tells you that 3v1 plus v4 is equal to 0, which tells you that v1 is equal to -1/3 of v4. v4 is -1, so this is 1/3. And v3 is still free, so the easiest choice is 0. So the solution, our v4 solution, is equal to 1/3, 0, 0, -1. Okay. So we have two diagrams. Let me redraw it. So we have two diagrams. So for lambda equal to 2, we use a different color. For lambda equal to 2, we have this one, and v2 is here. So we have 0, 1/3, 0, 0. This is v2 going to 1, 0, 0, 0, going to 0. And for lambda equal to -1, we have this chain, and v4 is here. So we have, this is v1. v4 is 1/3, 0, 0, -1, a plus I, which is going to be 3, which is 0, 0, 1, 0, and goes to 0. Okay. So the Jordan block, so A is equal to P, J, P inverse. P is the matrix with v1, v2, v3, v4 being the columns. First column v1, second column is v2, third column is v3, fourth column is v4. And J is almost diagonal matrix, so it's got two eigenvalues. So it's got a block of size 2 with eigenvalue 2 and a block with size 2 with eigenvalue -1. There's going to be a lot of zeros here, not that one. It's going to be a lot of zeros. So zeros below the diagonal and zeros outside of blocks. And because we have v2 going to v1, so this entry is 1. Signalized v2 is pointing to v1, and this entry is also 1. Signalized v4 is pointing to v3. So this is our Jordan block for A. And the general solution So x is, so there's v1, v2, v3, v4. For lambda equal to 2, we have c1. v1 is an eigenvector, so it's e to the 2t times v1. And v2 is a generalized eigenvector going to v1, so we have v2 plus tv1. And for v3 and v4 is lambda is -1, so we have c3. v3 is an eigenvector, so it's e to the -t times v3. And v4 is going to v3, so it's e to the -t v4 plus t v3. Alright, so this is probably as complicated as it gets. It could be, in theory, it could be more complicated, but this is as complicated as we're going to deal with in this class.